My name is Bassem Hassan. I work at the Paris Brain Institute. Welcome to my exp. We all start life as a fertilized egg that sort of divides and grows and grows and grows and grows and grows, and at some point, some part of that growth, it becomes what we would call differentiated. That is to say, that has a specific potential, in this case to become brain, but not something else. So the cells that are going to make your brain, at some point in embryonic development, stop being able to make anything else, and they can only make brain. And at that point, it's like a bit of a sheath, really, of cells like that. And it sort of turns on itself and becomes something we call the neural tube. It literally forms a tube, and we call that the neural tube. Now, the more frontal parts of this neural tube, or the more anterior parts of this neural tube, are what are going to become the brain, and the more back parts, more posterior parts, are going to become the spinal cord. Well, the hindbrain and then the spinal cord, right? And so the brain is this frontal part. And from that moment on, this sheath of cells, this tube of cells really now, are sort of competent to form brain cells. You experience new things. Those experiences have to be stored in as new information that may come useful and handy in the future, and that would be through formation of memories, or that might be useful and handy right now in making a decision. You know, I'm biking towards work, let's say, and then I realize that the route I usually take is blocked because, you know, there's work in the roads or a big demonstration or whatever. My brain has to immediately process the fact that I need to change my route and take some other route based either on my previous experience. So I have to retrieve my memories of how else do I get to work or wherever it is I'm going. But also what else might be on that other route that I'd have to deal with immediately. So I'd need a balance between stability and plasticity, keeping things as they are and changing them ever so slightly so as to be functionally useful. And so this process of maintaining the right balance between trying to keep things as rigid as possible because you've made a brain that works, and trying to keep on getting changes because you need a brain that works with an unpredictable environment, it might be referred to as, or is referred to as, a process of homeostasis. And homeostasis is just a word that means trying to keep the equilibrium, the balance of the system where it is optimal to deal with the environment. And so essentially, that's what we spend most of our adult lives doing, is trying to keep our brain in proper homeostasis. Essentially, everything that the brain really deals with during life, adult life, young adult life, sort of mid-adult life and aging, is built into it during those early months and couple of years of very early development, of embryonic fetal development and very early life. Everything that makes the brain what it is, makes it as functional as it is, but also as robust as it is, and also as homeostatic and redundant as it is, and finally, as vulnerable as it might be to certain types of problems, is actually built in it during development. And so that then brings us, sort of closes the circle back and tells us that the importance of understanding how the brain develops and what the different mechanisms and processes that play an important role in the development of the brain, why those are important is because they tell us something about how this brain will work for the rest of its life. A lot of people, just for simplicity, would refer to the brain as an electrical wiring circuit or a computer. That's what everybody likes to actually, the brain couldn't be less similar to an electrical wiring circuit, even though it's a circuit that is wired through cables, couldn't be any less similar to a circuit or a computer. And the reason for that is very simple. An electrical circuit of this apartment, let's say, or of your laptop or my laptop, is basically built on a blueprint. If you give an electrician or a computer engineer this blueprint, they will be able to reproduce it at 100% accuracy every time. So this map of an electric wiring diagram or the motherboard of a laptop is what we would call a map of total endpoint information. You can put it together in more or less any sequence, and it'll always be 100% accurate. The brain is not like that. The brain is what we would call a self-organizing entity. That is to say that there is no map of what the brain is going to look at. It's a self-building structure. It's a structure that builds itself and organizes itself according to a set of rules that are encoded in the genome. So what our DNA does is it tells our brain cells what are the rules according to which they can behave. And these rules, when those cells implement them, make it such that the brain develops the way it develops. So understanding those rules, what those rules are, how those rules allow the brain to develop the way it develops, is going to give us a lot of information about what makes the brain work the way it does, right? It's not about looking, or not just about looking at the final product that's going to tell us how it works. It's actually understanding the way that product came together in an absolutely fascinating, deeply still mysterious way, despite all the knowledge we have, that actually is going to tell us how this brain works and why it works the way it does.